Welcome to the algorithmic foundation of modern connectivity. Today, we dissect Dijkstra's algorithm, the greedy strategy that powers everything from global internet routing to the navigation app in your pocket. Our goal is precise. Identified a single starting point, we must find the cheapest possible route to every other destination in the network. Mathematically, we minimize the sum of edge weights, denoted as the path cost. Before we proceed, there is one non-negotiable rule. Edge weights cannot be negative. If a specific road actually pays you to drive on it, Dijkstra's greedy logic breaks down completely. This algorithm relies on a property called optimal substructure. Simply put, if the fastest route from New York to London stops in Paris, then the leg from New York to Paris must also be the fastest possible way to get there. Now let's look at the engine that drives the algorithm, a process known as edge relaxation.
We call this operation relaxation. Think of it like a string connecting 2 points. We check if going through node U offers a shortcut to node V. If the current distance to V is greater than the distance to U plus the weight of the edge between them, we update V with the new shorter value. Dijkstra is what we call a greedy algorithm. At every step, it blindly grabs the closest unvisited node, adds it to the settled set, and assumes, correctly, that no future detour could possibly beat this local choice. It never looks back. The life cycle of the algorithm is a continuous loop. We extract the minimum value from our priority queue, lock it into our finished set, relax its neighbors to see if we found new shortcuts, and repeat until the queue is empty. How do we know this greedy approach works? We prove it via loop invariance. We can demonstrate that at the start of every single iteration, every node in our settled set S already holds the true absolute shortest path distance, denoted as delta of S to V. The algorithm's speed depends heavily on the data structure used for the priority queue. A simple array is slow, taking V squared time. A binary heap speeds this up logarithmically. For the theoretical maximum, a Fibonacci heap runs in near linear time. However, the greedy strategy has a fatal flaw. If the graph contains negative edges, a path that looks expensive now might become cheap later. Since Dijkstra semmels nodes permanently and never rechecks them, it will miss these opportunities and return incorrect results. When negative weights are present, we must abandon Dijkstra and switch to the Bellman-Ford algorithm. Bellman-Ford is significantly slower because it relaxes every single edge repeatedly, but it guarantees correctness even in the chaotic world of negative costs.
This is not just academic theory. Dijkstra's logic is the heartbeat of the internet, powering the OSPF protocol that routes your data packets. It is also the core engine behind the GPS navigation that guides your daily commute. In conclusion, Dijkstra's algorithm balances the speed of greedy heuristics with the rigor of mathematical proof. It remains one of the most hard-working and essential procedures in the entire field of computer science.